All right, welcome back, everybody. We are in section 2.2, which is going to be some basic differentiation rules and then looking at some applications of rates of change. So when we're discussing rates of change, what we really are describing are derivatives, right? So derivatives are the rate of change of functions. So we'll start by discussing some basic properties here that are going to be used pretty fluidly. And the nice thing is that all of these are going to come from the properties of limits that we looked at in chapter 1. So a lot of these will carry over. So let's look first at a constant function. So if I have a function that is like y equals c, obviously, if we graph that, right? So if I have a constant function, what is the slope of that function everywhere? The slope is 0 because it's constantly the same value. It's never changing. So for that reason, the derivative is going to be 0 because the slope is constant. So also, if we take the derivative of a multiple times a function, so 10 times f of x, 6 times f of x, pi times f of x, just like with limits, the pi doesn't affect the derivative process, just as it doesn't affect the limit process. So we could write that as c times f prime of x, or c times d dx. So just note this d dx is just the operator for derivative. So differentiate with respect to x is what that is saying. So that will just be c times f prime of x. And then similar to our limit properties for two functions that have limits that exist. In this case, we have two differentiable functions. So if a function is said to be differentiable, that means the derivative exists on its domain, right? So if it's not differentiable, it would have to have some sort of discontinuity or sharp turn or vertical asymptote of that kind. So if both are differentiable, though, then the derivative of the sum is equal to the sum of the derivatives. Just like it was with limits, which we could just write as f prime plus g prime. And the same will be true about the difference. So this will be f prime of x minus g prime of x. Again, and we could actually prove this rigorously if we wanted to. So just as a kind of an example of how we could prove this. So if I took the derivative with respect to x of f of x plus g of x, that is the same as the limit as h goes to 0 of f plus g at x plus h minus f plus g at x all over h minus 0, which gives us our typical derivative description. And then we can kind of easily see how we can just separate and manipulate the terms on the top. So we'll get the limit as h goes to 0 of f of x plus h minus f of x plus g of x plus h minus g of x. So just distribute that negative sign and rearrange the terms a little bit. And then we know that both of these functions are differentiable, which means we can split the limits. And which gives us f prime of x plus g prime of x. So again, the book has a lot of these derivative kind of proofs. So this is what one would look like. They're a little bit trickier when we get to quotient rule and chain rule and product rule, but they run pretty similarly, where we want to split into a convenient limit that works out. So let's go ahead and talk about what's going to be one of your favorite rules, which is the power rule. And actually, probably most of you have seen this before. So if n is a rational number, then the function f of x equals x to the n is differentiable. So every polynomial and root function is differentiable on its domain. and the derivative with respect to x of f of x, again, where our function was x to the n, is equal to n times x to the n minus 1. Right? So our power rule, the reason for that is whatever your function looks like, its power becomes the leading coefficient. So it comes down in the front, and then we just subtract whatever the power was by 1. So n times x to the n minus 1. So this is super useful because you no longer have to use this. You no longer have to use the limit definition, as long as we can prove this. So we're going to have to prove this. But we can do that. It's not too bad. So we'll prove this just below here. But note, this is going to be the most common derivative that you run into because we're going to be dealing with polynomials quite a bit. Okay, so how do we prove it? Okay, so in order to prove it, we're going to have to use Binomial Theorem. So let's recall a little bit what that is, because it's probably been a while. All right, so if we look at a very nice pattern, I'll write out the first couple of rows of this. You know, what is this triangle of numbers called? Yeah, this is Pascal's triangle. Named after Blaise Pascal. So he did a bit of work with this pattern, although it was known before him as well. So if we continue on, so we can see that to get, if we start at the top, we start with 1, and then we put these 1s on the outside, and to get the next number, we combine any two adjacent numbers. Right, so 1 and 2 combine to give 3, and then combine again to give 3, etc., etc. And those will just continue on. So this triangle has interesting implications all across mathematics, not just in calculus, but in combinatorics, which is the study of counting objects, as well as probability and statistics. So most of you have probably seen the binomial probability calculations for if you flip a coin 50 times, what's the probability you get, exactly 35 heads, whatever it is. So the way we're going to look at this is as expansion of binomials. So what do I mean by that? Well, if I have two numbers that I'm expanding, so let's say x and y, there's an interesting pattern that you'll notice for different powers that you're expanding by. So if I have x plus y to the 0, that would be x to the 0 plus y to the 0, which x plus y to the 0 is just going to give you 1, right? Any number to the 0 power is going to be 1. We'll assume x and y are non-zero, so they're not 0. And then if I had x plus y, well, that's going to equal 1x plus 1y. And then if I have x plus y squared, we could write that out, right? X squared plus 2xy plus y squared using the distributive property. Oh, well, let me use a different color actually. X squared, xy, y squared. And another thing to note is that I could have reversed it. I could have done y squared first, right? So there's also a really, really nice symmetry to this expansion as well. Okay, and then if I had x plus y cubed, right, I get, this will now be x cubed, this will be x squared y, x, y squared, y cubed. So you can see that the sum of the powers, if I put little 1s here for the linear terms, the sum of the powers of any given term is going to be 3 in this case, or 2, or 1, or 4 if we went below and we had x to the 4th and then x cubed y, etc. So this really wonderful pattern. Now, there's also an additional pattern here that we can replace these numbers by combinations. So in other words, if I look at this row here, right, so this would be x plus y to the 4th. So we call this the 4th row of Pascal's triangle. And so what this would be is, if you remember from probability, we have combinations. So that's where we arrange objects where order doesn't matter. So let's just note, n choose k is calculated with this kind of wonky formula that you can derive. So we won't derive it here, but it's n factorial over k factorial times n minus k factorial, where the factorial is just the descending product. Right, so we go all the way down till we get to 1. So you take the product of every number n and every smaller integer from n down to 1. So you might be wondering, well, okay, well, why does this matter? Well, if you calculate these by each row, so again, this is the 4th row, that this is really 4 choose 0. This is 4 choose 1. 4 choose 1 is 4. 4 choose 2 is 6. So let's look at that. So 4 choose 2. So 4 choose 2 would be, and note this is n, this is k. So we've got 4 factorial over 2 factorial times 4 minus 2 factorial. So we can just verify. So 4 factorial is 4 times 3 times 2 times 1, which is 24. 2 factorial is 2 times 1. And then 4 minus 2 factorial is 2 factorial again. So then I get 24 divided by 4, which is 6. Exactly what we wanted there. Okay. So again, this won't be super important for our purposes because we're not going to use combinations really much for the calculus course, but it is a very useful pattern to simplify our proof when we get to our proof. So now we've got 4 choose 0, 4 choose 1, 4 choose 3, 4 choose 2, 4 choose 3, 4 choose 4. And those will give you all of the coefficients. So that means that if I went to the nth row of Pascal's triangle, I would get n choose 0, and n choose 1, and n choose 2 in each corresponding column, all the way down to the last term, which will be n choose n. And we'll note that n choose n is 1, and n choose 0 is 1. So we always get the ones on the outside. And then if I do n choose 1, I get n, right? So 4 choose 1 is 4, 3 choose 1 is 3. So those will be kind of the important ones that we want to look at. All right, so let's get back to our proof here. And the proof that we're going to use with the binomial theorem was really kind of originated with Isaac Newton. So he used this as his kind of proof, but it may have been known before him, but really was popularized by him. Okay, so up at the top here, I just have our generalization of those binomial expanded terms. So let's go ahead and take a look at the derivative with respect to x of x to the n. So we've got our limit definition expression, and this is our binomial expansion. This is what we need to use the binomial expansion formulas for. So we'll do limit as h goes to 0, and again it's n, so I'm going to start with n choose 0 times x to the n plus n choose 1 x to the n minus 1 times h to the first, right? So I subtract 1 degree from the x, and then I add 1 degree. If I add those together, I'll still get n. And then I'll have n choose 2, x to the n minus 2 times h squared. And we're going to continue in this fashion, right? So all the way down to the very last term, which will be n choose n, x to, or not x, there won't be any x's left, it'll be x to the 0, and then h to the nth power. Okay, so that's my expansion of x plus h to the n. And then let's not forget that we're subtracting from that x to the n. And it's going to be all over h. So a whole bunch of stuff over h. So now, whoops, if we move our work down below here, let's see what we get in that numerator. So n choose 0 is just 1, so I get x to the n. N choose 1 is just n, and then I have x to the n minus 1, h to the first. And then the rest I'm going to just kind of ignore. So then the rest I'm just going to leave as is. So this is going to be n choose 2, x to the n minus 2, h squared. And we'll see in a moment why I don't really need to worry about those. And then we'll add in, so this last term, or second to last term, sorry, is just h to the n, because n choose n is 1, minus x to the n. All right, so we got all that. And we'll note we get this very beautiful cancellation of x to the n, which means if I look at every remaining term will have at least one h in it. And that is the key. So now I'm going to factor an h out of each one of those terms. So we're going to have h times n x to the n minus 1 plus n choose 2 x to the n minus 2 times h to the first, because I took one h out. And then again, we'll take an h out of every remaining term, and then we'll end with h to the n minus 1 all over h, which cancels, which means the limit as h goes to 0 of all of that stuff it's going to work out very nicely, because if h is 0, all of the terms except the first go to 0. So my resulting limit then is n times x to the n minus 1. And that concludes our proof. So really, really, really nice result. This is not the only way to prove it. There's tons of different ways you can prove the power rule, but this is the one that I think is a really nice, elegant one using that limit definition. All right, so I think that'll be a good place for us to stop. So next time we'll look at the examples after this. So if you have questions, definitely send me an email or come by the office hours. Otherwise, until